Last time we began our discussion on bifurcations, and we ended with looking at how to find the extended center manifold and the equation of motion along it. So we hinted at, normal forms and said that we would talk about them next time. So that's what we're going to do today. We're going to start with the structural stability of bifurcations and the genericness of the saddle node bifurcation. So to look at the structural stability, we'll consider adding a small perturbation. So epsilon with modulus much less than 1 to the right-hand side of the system for each type of bifurcation. And then we're going to Taylor expand and analyze, what happens when we perturb the system. So we'll start with the saddle node. The saddle node has normal form x dot equal to mu minus x squared, and this is for mu greater than 0. We could alternatively say it has form mu plus x squared for mu less than 0, or something like that. And so we can see from this that if we wanted to find the fixed points, so where x dot is equal to 0, hold on, my laser's not working. There we go. Yeah, so we wanted to find the fixed points where x dot is equal to 0. We could factorize this into, difference of two squares. And so the fixed points would be x equals to plus or minus root mu, which we've seen before. Looks like this. We also know how to show the stability of these two by considering some test point and using continuity arguments. So we find that this upper branch is stable and the lower branch is unstable. If we were to then perturb the system to analyze the structural stability, so let's add a small epsilon, positive in this case, to the right-hand side. And we can do the same thing here where we factorize it as the difference of two squares. And if we plot that in the mu x plane, we get something that looks like this, which, is topologically the same as the case where epsilon is equal to 0. And so that shows us that the saddle node is topologically invariant under this small perturbation. And so we can say that the saddle node is structurally stable. Does that make sense?
Yeah, I think so.
Great. So in fact, we'll see that the saddle node is the most generic bifurcation. So by that I mean that if we perturb other systems with bifurcation points, so say transcritical or pitchfork, if we perturb those systems, then we're also going to sometimes end up with saddle nodes or with no bifurcation at all. So we'll look at transcritical next. It has a normal form x dot equal to mu x minus x squared. Again, we can just take mu greater than 0 here. Or alternatively, we could say for mu less than 0, we have mu x plus x squared. So either of those work. We can factorize this, and so this gives us the solutions x equals 0 or x equals mu for the fixed points. And so this is that plotted on the mu x plane, and this is what we've seen before. So this is what transcritical looks like. We have two different fixed points and they collide and exchange stability. So to analyze the structural stability, we perturb the system, adding a small epsilon. This time we'll add a small epsilon which may be positive or negative to the right-hand side. And we get this quadratic, which we can solve using the quadratic formula to get two solutions here and a solution, sorry, just two solutions here. So if we plot these solutions for epsilon less than 0 or greater than 0, it turns out we get graphs that look like this. And yeah, you can check this by yourself, I suppose, if you want. But I guess a quick sanity check is if for, in the case, epsilon greater than 0, let's say I plug in mu is equal to 0 into this above form, then I'm going to indeed get plus or minus root epsilon, which is what we have here. We can do a similar thing over here. And when we plot these graphs, we can quickly tell that these two are saddle nodes in the epsilon less than 0 case. And for epsilon greater than 0, we actually end up with no bifurcation, because this fixed point here, it might change x position, but it stays stable. And this below fixed point here, it changes x position, but it's still unstable. So nothing topologically happens to this, like nothing topologically changes in the system. Yeah, the thing to be careful of here is if you're doing an exam question on this and you find a normal form, it might not be exactly this. So you can't just memorize, say, for epsilon less than 0, we get 2 saddle nodes, and for epsilon greater than 0, we have no bifurcation. You'll have to check that by yourself. And so from this, because the topological structure of the system changes, a transcritical bifurcation is not structurally stable. And the reason why, one of the supporting reasons for saddle node being generic is, as you can see here, when we perturb by a small negative epsilon, we end up with 2 saddle nodes. Is that okay?
Yeah, that makes sense.
Yay. So we'll move on to pitchfork now, and we'll look at 2 different perturbations of the pitchfork bifurcation. First of all, just a normal one where we add just a constant epsilon. So the normal form of the pitchfork is mu x minus x cubed equal to x dot. And so if we factorize this, we get the 3 fixed points. We have x equals to 0, which runs through the middle here. Let's actually label these. We get the top branch, which is x equal to root mu, and we have the bottom branch, which is x equal to minus root mu. And of course, the fixed points plus or minus root mu only occur for mu greater than or equal to 0, which is why we get this bifurcation point here. Yeah, so if we perturb this system with a small epsilon that may be positive or negative, just a constant epsilon, then we have cubic, which I'm not going to bother solving for brevity, but if you were to plot it, then you would get this for epsilon less than 0, which has a saddle node, as well as a point that does not go through a bifurcation. And for epsilon greater than 0, the same thing, but kind of upside down. Again, we can see that when we perturb a pitchfork, we end up with saddle nodes, showing again that it's the most generic bifurcation. And of course, the pitchfork is not structurally stable because topological structure isn't preserved. So now we'll move on to the last one in 2D, which is, it's just another illustration of the instability of the pitchfork, I suppose. Instead of adding a constant epsilon now, we're going to add a small quadratic term. So a small epsilon times x squared, where epsilon again can be positive or negative. So yeah, I guess the procedure is quite familiar by now. We just add in this epsilon x squared term, and then we can factorize this into, well, x equals 0, or we have some quadratic equal to 0. So we can use the quadratic formula to solve for this. And so we get, as you would expect, the x equals 0 solution, and then the solution given by the quadratic formula. So yeah, when we perturb with a negative epsilon, this solution given by the quadratic formula just shifts downwards, and also in the negative mu direction. And similarly, for when epsilon is greater than 0, we shift upwards. And yeah, it's basically, you can imagine it's this part shifting. And so you would expect that because this intersection no longer lines up nicely, we get a saddle node and a transcritical. like this. And I guess I haven't verified this, but my intuition would be if we were to now add both a constant epsilon, as well as say a quadratic delta term, then we would have this shift, but also the transcritical bifurcation would also be destroyed. That's what I believe would happen. Yeah, does that sound good?
That does sound good. I'd be interested to see a little like sketch of what that might look like if we had both of those things happening.
Okay, well, I can't guarantee that I'm correct with this, but we can try. In fact, why don't we just try doing it? Yeah, so the PF, we have mu x minus x cubed. Let's try that. And let's add a perturbation with, let's say, plus epsilon, and let's say plus, why have I got partial operator? Plus epsilon plus, let's say, delta x squared. So now we have x dot is equal to epsilon plus mu x plus delta x squared minus x cubed. Okay, well, I suppose this might be quite difficult to solve, actually. Which I didn't think this through very well.
Yes. Sorry, I'll give you.
Okay, now let's just imagine that we can write it as, say, minus x minus a, x minus b, x minus c for some a, b, and c.
Yeah.
I'm not sure if this is going to work, but we can try. Okay, what would that tell us exactly? Yeah, it's hard to tell because, you know, the B's and C's, the A, B, and C might be in terms of epsilon and mu. In fact, they would be. Okay. Well,
Yeah,
I don't really know what happens.
in general,
it
makes sense that this is going to depend on what ratio the perturbations are in. So I suppose it's unreasonable to hope for like a general thing, because if you had if the quadratic perturbation was like 10 times the linear one, maybe it's completely different. So okay,
I mean, no, I think it's good that we looked at it because I don't think they can feasibly ask this in exams. It doesn't look like it's very easily factorizable, and but if I were to guess what happens, I mean, I'm sure this can happen. I'm just not sure like what epsilon and delta you would have to pick. But I suppose. Okay, so this was the picture we had before with like kind of a saddle node and the transcritical. Let's draw that better. So I suppose if that were perturbed, you could end up with, for example, I think we could get this and this, right?
Okay, with it being stable.
With this being a saddle node and this just being no bifurcation.
Oh, okay.
I haven't drawn the stabilities in because, well, yeah. Or if we put, I don't know, I'm just drawing some ideas of what could possibly happen. I don't think this is really just for interest at this point. Yeah, I wonder if this is possible, where we kind of get a saddle this way and a saddle that way.
So where would those which diagrams are those two saddles coming from? So in the kind of basic like standard form cases, which two saddle nodes are you kind of hoping to extract and like combine?
Oh, like from this?
Yeah, so you got that one, and another one from another case.
Yeah. As in general, when we perturb things, it's like you can imagine this like.
It pulls apart the red
it just
line.
pulls apart in some direction.
Yeah.
Which is why I was saying it can either. Let's draw this better. I was thinking it could either pull apart like this, or it could pull apart like this, which is where these two things have come from.
Yes.
Yeah, but again, I'm completely not sure about that, and I haven't seen anything that looks like this before, so I'm not even sure if this is possible.
Okay.
Yeah. Okay, let's move back to the main content. Right, so the next thing we'll look at is actually the last thing here, which is the oscillatory / Hopf bifurcation, which is, I think it's basically just a 3D pitchfork, and you'll see why I think that. So yeah, the normal form looks like this. It makes more sense when you look at it. So I think it's best explained with pictures. So yeah, a is equal to plus or minus 1. In the case a is equal to plus 1, we get something called supercritical Hopf bifurcation. And it looks like this. So we have x in this direction, y, and mu is varying along the horizontal axis. So yeah, for mu less than 0, let's think about it here, right? For mu less than 0, okay, let me actually write this out. So this will be, okay. So I think it's minus 1 over a r squared minus a mu r, which is minus 1 over a, r plus root a mu r minus root a mu r. Yeah, so this tells us r dot, right? So if mu is less than 0 here,
sorry, yeah, where are we adding mu? Oh, sorry. It's in the, never mind, it's in r dot.
Yeah, if mu is less than 0 here, then we don't get any solutions here for r because r is clearly greater than 0 and it's real. So the only point with r dot equals to 0 must be r equals to 0. So that is our only fixed point for mu less than 0. And that turns out to be a stable fixed point that we spiral into. We can show that we spiral into it if you plug in some point that, say, r equals 1, and we have mu less than 0, and you'll basically find that r dot is less than 0, which means that, we're decreasing in r. And for mu greater than 0, you get 3 solutions. So you have r equals 0 as before. We have r equals we just get r equals root a mu because r is clearly positive. In fact, let me write that here. So r equals root a, root mu actually, because a is equal to 1. So essentially, as mu increases here, we're getting a stable periodic orbit at each value of mu that has radius root mu. So again, don't think of this as a 3D system. Think of it as, if I want to know what the system is doing at some value of mu, I'm going to take a slice through the system. So I guess, for example, if I took a slice through, what color do I do this in? Let's take a slice through no. Yeah, let's take a slice like this. Then basically what this looks like in the XY plane is we have a fixed point at the origin, we have a periodic orbit, and inside the periodic orbit we're spiraling away from the fixed point, and outside, let me do this in different colors, this is terrible. Like this, and outside the periodic orbit we're spiraling into it. So yeah, that's kind of like what I mean by take a slice of the system for some value of mu to find out what's actually happening. Does that make sense?
Yeah.
And then on the other side, like if I take a slice like here to see what's happening, that's quite clear. So it's just we have a stable focus at the origin. Yeah. So that's what's happening. Yeah, so do you see what I mean by it's kind of like a 3D pitchfork?
Yeah, it makes sense.
Yeah, instead of having like a 2D envelope of just there's two fixed points to either side, so one fixed point to either side, we now have a periodic orbit acting as an envelope. So, you know, I guess you can say a stable fixed point, right? Changes stability and sheds a stable periodic orbit. That's what you would say. And I think of it as, you know, if it's supercritical, then the envelope is stable. And if we have A equals -1, we have a subcritical Hopf bifurcation in which the envelope is unstable. So they look at pretty much the same, except the stabilities are swapped.
Okay, but it's still periodic. Yeah, so it's still periodic orbits, but you go
Yeah,
away.
but if you perturb away from it, then you're going to move away from it. Whereas with this stable PO, if you perturb away from it, you move towards it. Yeah, I think that's really it. As long as you like kind of remember the normal form. I don't know, maybe you don't have to remember it, but it's probably good too. Although I think sometimes they'll give it to you in an exam question, and it's more likely that they want you to recognize the form. Just a note here, I've drawn the spirals, you know, in just an arbitrary direction. When you do actual questions on this, you'll have to check what direction, like clockwise, anti-clockwise, the arrows are going in based on the value of theta dot. So yeah, make sure you check those. And yeah, just to end off with, there's a little bit of an exam tip that our lecturer actually did this as part of a non-examinable section, but I thought that it was quite useful. So the tip is this: if you want to see the radial dynamics for different values of mu, so like for example, if I want to find out that I have a stable PO here, or you know that I have an unstable PO here, or that I don't have any POs, then I'm going to take, for example, my system, and I'm going to plot an R dot graph. So a plot of R against R dot. So for example, here with mu greater than -1/4, you can convince yourself that this is true. I'm taking this equation and I'm just plotting it. So you get, well, a quintic function. And what you do is you say, well, when R dot, right, is below the R axis, is negative, and therefore we're flowing this way in the negative R direction towards the origin at 0. So we draw in an arrow there, we draw in an arrow here because we have positive R dot, and then here we draw in a negative arrow because R dot is less than 0. So that helps us to classify stabilities, because clearly whenever this function crosses the R-axis, that is a fixed point or a PO, because we have R dot equals to 0. So if we're at that point, we're not going to leave that radius, right? And so what 0, we have an FP, and if R is not equal to 0, when R dot is 0, we have a PO, because, well, yeah, we're going to stay on that circle. Then now the arrows tell you whether that PO is stable or unstable. So I thought that was quite a neat trick.
Yeah, nice.
And yeah, if you want to see the corresponding picture of this above example, stable FP, unstable PO, stable PO, and so we have the arrows, yeah, going in the correct directions. Again, note that for the direction, you would have to look at theta dot, and I've just drawn this direction as an example. Yeah, that's it.